This lecture is on dominance, and these are the topics that we will look at today. So we begin with the formal definition of a normal form game. A normal form game is a three-tuple consisting of n, a set of agents. I use scripts for sets, and the cardinality of this set n of agents is n, and each agent has an action set a sub I. So this is the set of actions of the ith agent, or I usually refer to it as action space. And pi I is the payoff of each agent I, and that's a mapping from the joint action space to a real number. And lowercase a sub I is any action, and this is the joint action of all agents A1 through AN. And so for each joint action, each player or each agent I receives a payoff. So here's an example of a normal form game. This is a bimatrix game, and there are two agents, agent 1 and agent 2. So n equals 2 here, and agent 1 has actions A, B, C, and D available to it. Agent 2 has P, Q, R, S, and T available to it. One possible action for agent 1 is B, and one possible action for agent 2 is Q. So a joint action is BQ. What are the payoffs for this joint action BQ? Agent 1 is playing B and agent 2 is playing Q, so these are the payoffs. Payoff of agent 1 is 7 and payoff of agent 2 is 8. Now here's some notation that's very specific to game theory. A subscript negative I is the action space, the joint action space of all agents excluding agent I. So these are the opponent agents. Negative I is the set of all agents in N except agent I. And so this is the joint action space of the opponent agents. And lowercase a sub I is any one joint action of all the opponents of agent I. And a joint action of all agents, that is, can be written as AI, comma A negative I. This is rather deviation from the standard notation, because A sub I should be here, but I've put it right at the beginning. That's acceptable notation in game theory. Dominance. An action AI dominates another action AI prime, denoted this way, if and only if for every opponent action A negative I, agent I's payoff with action AI is always greater than equal to its payoff with A prime I. Replacing the greater than equal to with the strictly greater than sign, we arrive at the condition for strict dominance. As an example, consider this bimatrix game. Now, look at agent 2's payoffs under P and Q. The payoffs 3, -1, and 3 are element-wise greater than 0, -2, 0. Therefore, P strictly dominates Q. And likewise, 3, -1, 3 is element-wise greater than -2, -3, 1. And so P also strictly dominates S. Therefore, Q and S are redundant. The agent 2 is never going to play any of these actions. So we can simplify the payoff matrix by simply eliminating columns Q and S, resulting in this simpler payoff matrix. Now this simpler matrix reveals some new dominance relationships. A strictly dominates B because now looking at the payoffs of agent 1, 3 is greater than 1 and 4 is greater than 2. And A dominates C also, but it's not strict dominance. Now, since B is strictly dominated by A, we can also remove this row from the payoff matrix, resulting in an even simpler payoff matrix here. It should be noted that after the application of this elimination of strictly dominated actions for both agents, the Nash equilibrium points were never eliminated. That's an important observation. This is the IESDA algorithm. At first, a Boolean flag change is initialized to true so that the while loop below it executes at least once. The while loop will be executed as long as the flag change is true. The algorithm terminates when the flag becomes false. This occurs when none of the agents have any remaining strictly dominated actions. Within the while loop, the change flag is reset to false. It will be set to true later only if some agent has one or more actions that are found to be strictly dominated. The inner for loop is repeated for each agent I. First, each action AI is tested to see if it is strictly dominated by any other action A prime I. The set DI is the set of all such strictly dominated actions. If DI is not empty, then agent I has some remaining strictly dominated actions. These actions are removed from agent I's action space, and then the change flag is set to true. The process continues until termination. The Nash equilibrium action is denoted A star, and A star sub I is any agent I's Nash equilibrium action, and A star sub negative I is the joint action of the opposing agents. So at pure Nash equilibrium, for every action AI that's not the Nash equilibrium action, the payoff pi I with action AI will always be less than equal to that payoff with the Nash equilibrium action AI star. Replacing this less than equal to with a strictly less than, we can get the definition of a pure strict Nash equilibrium. Let's recall the condition for strict dominance. AI strictly dominates A prime I if for all joint opponent actions the payoff with the dominating action is always greater than equal to the payoff with the dominated action A prime I. Now, actions at Nash equilibrium are not strictly dominated. Therefore, IESDA, iterated elimination of strictly dominated actions, cannot eliminate Nash equilibrium. This is an important point to note. And this can be formally stated in the form of a little theorem here. So, for all actions AI cannot strictly dominate a Nash equilibrium action A star I. And the proof by contradiction is quite simple. We assume that there exists some action AI that actually strictly dominates A star I. Then we can apply this here, this expression, where A prime I is replaced with A star I. So this relationship holds. This greater than relationship holds, which we write here. And now, since this relationship is valid for all opponent action A negative I, it must in particular be valid for the opponent Nash equilibrium action A star negative I. And so we replace A negative I with A star negative I, and so we get this expression here. This relationship is again strictly greater than, and this is in direct contradiction to the definition of Nash equilibrium, because here you have a less than equal to sign, here you have a less than sign, and here you have a greater than sign. So this completes our little proof.